you for that stimulating introduction. Can you hear me at the back? Okay, that's great. Oh, that's good acoustics. Well, in being asked to give you a talk that had the word volcanoes in it, I thought, why don't I try and get really relevant and give you my perspective on this particular topic. I have to press some arrows here instead. Whoops, just a bit slow. In explaining the title of this talk, I do need to explain just one piece of terminology, and that is when we use the term volcanic risk. By that we mean that there may be a volcanic hazard, which is what I will largely talk about tonight, but you also have to take into account when you're assessing volcanic risk, first of all the value of whatever it is that is at risk, and secondly its vulnerability. So something that is a long distance away will obviously be less vulnerable than something that is proximal. And so just take that into account when we talk about risk. In this slide, I've got the various volcanoes that are likely to impact the Whanganui region. And we can see, of course, the Taupo volcanic zone here. I'm not going to go right up to the Bay of Plenty, but we'll start from Mount Tarawera here, and we work our way down through Taupo volcano. There's obviously Tongariro, Narahoe and Ruapehu, and we have Mount Taranaki or Mount Egmont lurking out to the west. Now, the way I thought I'd treat this is just to give you a very brief introduction. This is the map that's been compiled by NIWA these days of what is now being called the sort of equivalent of the New Zealand subcontinent, called sometimes these days Zealandia. And all the reds and pinks and yellows represent what is continental crust. But as you see, the New Zealand landmass is a relatively small proportion of it. And when you add up the amount of continental crust that there is, it's actually something like half the area of Australia. It so happens this is probably the largest submerged continent on Earth for a number of reasons that we won't go into tonight. Because the critical thing is that running through the region is a boundary between two of the Earth's largest plates, and this is the boundary coming down off the east coast of the North Island. It swings into Marlborough, goes along the Alpine Fault, slicing diagonally through to Westland, and it just runs offshore north of Milford Sound and then continues on down in this direction. We don't need to worry about the southern part here. The bit that relates to us is the North Island. And in the North Island, the model for understanding what's going on here is that we have the Pacific Plate coming in from the east, and because it is cold and dense and very old, having been made at a spreading centre way out in the middle of the Pacific, it is of greater density than the continental crust, which is forming the eastern edge of the Australian plate. So here we have the Pacific Plate diving down, and the reason that we have volcanoes in this part of the world was initially people thought the plate was melting, which is not correct. But what we now know is that there are a lot of sediments on top of this plate, since it's been out in the ocean for the best part of 100 million years, and these sediments come down sitting on top of the plate, and in this zone just about here, a lot of the sediments have clays in them, and these clays release water, and the water is driven off from the top of the plate, and this causes partial melting of the soup of mush that sits in this position, and this is what actually generates the magma that can then rise up towards the surface. And because of the way in which this process operates, there's some tension in the continental crust above, and this leads to the volcanicity that we see. So having explained the situation, let me begin from the northern end first. I mentioned Okataina or Tarawera and the Taupo centres because they are the two large, what we call rhyolitic centres in the North Island, which have the potential when they erupt to spread ash across this region. And this is a list, for example, of the rhyolitic tephras which are found in the Ruapehu district in, shall we say, the headwaters of the Whanganui River. Of these, TVC stands for the Taupo Volcanic Centre, and OVC is the Okataina, which includes Mount Tarawera. And you'll see they're dominantly from the Taupo Volcanic Centre that we find them. And you can see here that on average there's one of these events every 1700 years or so. And if we were to look at specifically Taupo, then there's on average one event every 2,500 years. We've had, come on in, we've had...
Sorry.
No, that's all right. We've had statisticians doing work on the frequency of these eruptions, and they've come to the conclusion that at this point in time we can't actually do a statistical analysis because the pattern is so irregular. So they reckon that in about 5 years' time, when they spend a whole lot more money, they'll be able to give us an answer to that. But it's, that's not my speciality up in the north. But I will mention one thing, just to give you some perspective on this. Here we have the bathymetric map of Lake Taupo, and we can see it's got a maximum depth of about 200 metres. It's thought that the deeper blue area was the centre of the last eruption just 1800 years ago, which was a cataclysmic eruption, there's no question about that, but these occur at infrequent intervals. To give you some perspectives on this, this is the Taupo eruption around the year 200 AD, and the largest eruption that we've had in recent times to compare with this was the Mount Pinatubo eruption in the Philippines in 1991. You can see smaller again was the Tarawera eruption in 1886. Mount St Helens here was in 1980 was smaller again, and the Ruapehu eruptions in 95-96 were infinitesimally small compared with all of these. The largest eruption over the last couple of hundred years on Earth occurred in Indonesia at Tambora in 1815, and this certainly had an impact on the world climate in both hemispheres. But let's put all this into perspective, that the previous large catastrophic eruption of Taupo, which occurred about 26,000 years ago, was 10 times the size of Tambora. It was 100 times the size of the Taupo 200 AD eruption, 1,000 times larger than Mount St Helens, and 10,000 times the volume of Ruapehu in 95-96. So these are the sorts of events that have occurred in the past, but as we say, they have occurred infrequently. That eruption 26,000 years ago spread ash across most of the North Island, parts of the South Island, and went out to the Chathams. Even in the Chathams, it's almost 20 centimetres in thickness, and in much of Hawke's Bay, it's over 200 centimetres thick. And unless you've got an eye in for these things and people point them out to you, you pass them in road cuttings and you don't even notice. But to give you an idea of the current situation, when we get a Taupo eruption of that nature, we get these very large, hot, gaseous flows. And this is, in my view, one of the better pictures that's ever been taken by anyone who survived one. This is taken from the Clark Air Base in the Philippines during the eruption of Mount Pinatubo. And Mount Pinatubo is about 10 or 20 kilometres in that direction. Most of the ash has gone up into the atmosphere, but these are hot avalanches which are running down valleys. This one's actually coming towards us, and that one's going at right angles to us, and we can see that these are extraordinary events. Well, in the Whanganui River catchment, we can see the impacts of this if we went to, for example, Timairi, which is labelled up there. Then these photos, this is near Timairi, and we can see the terrace that was formed by the Taupo hot flow. And at the Timairi gauging station, the top of the actual flow is in about this position here, and on the upper part there's a whole lot of resorted, water-sorted pumice, which of course came flooding down the Whanganui River, and is about 1 metre thick in the vicinity of Aramaho. So we know that there's an awful lot of redeposited pumice alluvium in the catchment, and clearly when large volumes of pumice like this are deposited, it's not just the hot flows themselves, but the fact that they destroy all the vegetation, and as soon as we get some rains, it's unconsolidated and is transported in large pumice floods. These pumice floods, incidentally, also went down past Hamilton in the Waikato River catchment. And I've plotted on here where those hot pumice flows have come into what is the Horizons region, the Manawatu Whanganui region, and only this last weekend have I been into the Retaruki, and to my surprise there's a whole lot of them in here as well, which I didn't know about until 2 days ago. So these would explain why there's so much pumice that came down the Whanganui at the time. Also, there's a pumice, great massive Taupo pumice alluvium at Flock House in the Rangitikei catchment, which came down there. And further down the coast, there's an entire line of sand dunes here that are filled with Taupo pumice, where the pumice got blown onto the beaches and blown inland. So there's Mount Pinatubo at the Clark Air Base in 1991, and hopefully we don't get to see anything like this, but this is what happens if you're driving your car and you're trying to get away from a pyroclastic flow. The car won't go fast enough. Now I'll turn my attention to the west. Mount Egmont, or Mount Taranaki, is one of the sources of volcanic ash which could impact the Whanganui region in the future. We've spent the last 40 years mapping the lava flows, which you see on the left, and mapping all the various deposits from landslides, and there are some hot flows, they're not pumice flows, they're hot rocky flows, and there are these large landslides and volcanic mud flows, or lahars, that you can see all spread out from the mountain, and this mountain has been collapsing on numerous occasions. The ground hugging flows have never really come beyond Hawera here, so it's actually the volcanic ash which is likely to have an impact in this part of the world. Now, as part of a civil defence series of booklets, we were encouraged to try and produce a hazard map for volcanic ash from this part of the world. And what I'm really going to draw your attention to are these diagrams on the right, because these are diagrams that come from Ohakea, and they're from wind balloons that get sent up determining wind direction at various altitudes. And you can see that over the time period that these measurements were made, the wind is dominantly northwest between 1,000 and 2,000 metres altitude, and when we get up between 3,000 and 10,500 metres, it's dominantly westerly, and when we get to 12,000 to 16,000 metres, again it's almost entirely westerly with small deviations to the northeast and the southeast. So if there were any more eruptions from this particular volcano, they are coming our way. Now, you might laugh at this, but to give you but one example, one of my colleagues did a PhD looking at this particular soil, which is on the campus at Massey University, and began looking at the minerals in the soil. And it was thought to all be wind-derived from blowing out of the riverbeds, but what we can tell you is at each of the red points on this diagram, we have volcanic ash that's come from the rhyolite centres, so it has to have come from Tarawera area or from Taupo. And the blue represents andesitic tephra, which has had to come from either the Ruapehu region or Mount Taranaki. Well, subsequent to that work, here's a published diagram from a core that was obtained from Lake Tutira in northern Hawke's Bay. And here I've marked in red triangles the volcanic ashes that are identified in this core that have come from Mount Egmont or Mount Taranaki. And so you can see that in the last 8,000 years, 3 of those volcanic ashes have made their way to northern Hawke's Bay. I've just given a couple of quotes here because this is also relevant to the story, and that is that researchers from the University of Auckland have been studying layers of sediment at Lake Pupuki on the north shore there, which is a crater that was formed about 250,000 years ago, or 250,000 years ago, and they've begun to find layers of ash from Mount Taranaki, which up there suggested they were getting eruptions from the mountain at intervals of around one every 400 years, getting to Auckland. Now think of the impacts on Auckland International Airport. And in more detailed studies in 1995 that I did with Brent Alloway, we were able to show that using the ring plane record around outside the national park, there were 76 tephras that had been erupted from the mountain between 3 and 28,000 years ago, which means there's an average periodicity for these eruptions as frequently as, on average, one every 330 years. And we do regard this, this figure as a minimum because there are a lot of smaller eruptions, but they didn't deposit ash outside of the national park. So, after we'd done that study, that led to more and more students wanting to go into the national park. Or, another technique was to find some lakes which were recording these volcanic ash layers. And this led to the discovery of a lake here in near New Plymouth called Lake Amutakai. And in this lake, we were able to find 104 volcanic ash layers. Another 45 of them were also found in Lake Rotakari out here south of near Eltham. And there were 23 other volcanic ashes or tephras nearer to source. And here's our sort of prevailing wind direction, and from this, it's this sort of record that encouraged people to start looking at statistical analyses of, because you had so much data, you could perform statistics on it. And we now have a professor of geostatistics at Massey University, Mark Bevington, and he began constructing these diagrams and looking at what was the probability of another eruption from Mount Egmont, Mount Taranaki, and the easiest way to express this is what's the chance in the next 50 years. The statistic of probability varies a little bit depending on what period of time you consider the eruptions. And when he first published this work, it was based on the eruptions over the last 6,000 years, and he came up with a number which was 66%, 0.66. It's interesting, the red curve has only come out as a black one, but this should be red here. And that was back to about 10,000 years. And I talked with him yesterday, and he said that the figures moved around a bit, but at one stage it was 50%. It's now, he thinks, about 60%. So a 60% chance of Mount Egmont, Mount Taranaki erupting in the next 50 years, which is more than the proportions of flicking a coin. Okay, let me move away from the Taranaki source and move to the Tongariro volcanoes as they're grouped. The one in the north, Tongariro, has not been particularly active with respect to volcanic eruptions, but this is a photo taken in the 1890s. It's in the Dominion Museum collection, showing the vent of the upper Timari crater erupting in front of Lake Rotowaira. And here's a postcard I discovered one day which had a print on the stamp at the back that was early 20th century. So this clearly is a sketch that someone's made of, you can see Ruapehu in eruption, you can see Narahoe, we can see the Ketatahi Springs, and also Timari just there. Well, that eruption, incidentally, from this crater, I mean this is post-eruption in 1896, a chap at Hill Henry Hill in Napier wanted to put on record that a storm of volcanic dust fell in Napier on the night of the 14th of December 1896 and early in the morning next day. So we know that these eruptions spread around, and of course where that star is, that's the Upper Timari crater, well then we had it erupting in 2012, and this was the first eruption was during the night, and ash fell across into northern Hawke's Bay, and this was the second eruption that occurred during the daytime, where a bit of a surge came out, which is highly destructive, and some of the boulders thrown out in this eruption went through the roof of the Ketatahi hut. But these sorts of eruptions are not really going to impact this region unless the wind happens to be blowing in the wrong direction. That only occurs in a small number of times, but if there were a nor'easterly, then the wind would blow it down into this part of the world. Narahoe, further to the south, was continually active until the 1970s, since when we've not seen anything happen at all. And I had a student working up there on a SAWS project one day when he looked up and saw this happening. And in this case, this photo was taken about 15 minutes after this one. And we can see a great column of steam and ash being carried high into the atmosphere. And then the steam dissipates, and this is the actual ash, which is on its way to Hamilton. And so that was deposited across the Waikato. But not disastrous by any means. And we know that Narahoe has been doing this for about 3,000 to 4,000 years. This is an eruption from Taupo about 3,300 years ago, and all these little grey beds that you see in here are a multiplicity of small eruptions that have come from Narahoe. Again, if eruptions of that size were to occur when the wind is blowing from the northeast, then they would blow down into the Manawatu-Whanganui region. So, let's move on then to where our talk is centred on Mount Ruapehu. Because Mount Ruapehu has had an impact in the Whanganui region in the historic past. Beginning with volcanic mudflows, or lahars as they're called in Indonesia, and this is a photo taken during the 1995 eruption, if I remember rightly, which shows downstream of Tangiwai the lahar flowing around a private bridge running across the Whangahu River. And you can see what a lahar is all about. It's a particularly dangerous fluid because it sucks things in as it flows by. And I heard a description of one person watching a lahar in 1975 when he saw a duck land on the surface, and I guess the duck didn't know the difference between lahars and water, and as the duck landed it disappeared into it. And so these have a large concentration of boulders in the base, and then it's a mixture of mud. It's quite a high concentration of sand, and it flows much more like porridge than it does like water, and this makes it particularly erosive and dangerous. And the reason for this, of course, is that Ruapehu, unlike the other volcanoes, has a crater lake. And this volume of water up at 8,000 feet, or 2,500 metres, has so much potential energy when it's released in coming all that altitude down the mountain. To give you an example of what we're basing our studies on, this is a drain that was cut by the forestry people about 20 years ago now. It's just upstream from the Tangiwai Bridge. But when they cut this drain, here's the sequence of larger lahars that's preserved in this swamp. And first of all, we can see the deposit from a fairly substantial lahar in 1861, which I was reminded yesterday was probably the first lahar ever described in New Zealand from the lower Whangahu River. And one of the farmers there saw it coming down, and he didn't realise at the time that the big white lumps in it were actually blocks of ice and snow. And as it went past him, it gave him a surprise, because suddenly he began to shiver, and it was carrying all this cold air with it as it passed him by. And then finally, as it started to subside, he talked about all the Maori canoes that had been washed away from the riverbank along the channel. Well, we can see that flows like 1861 but bigger occurred 450 years ago, 1300 years ago, don't worry about the numbers here, 1500 years ago. Here's the Taupo Pumice at 1800 years ago, and there's another unit in there. And then we can see a big landslide that turned into a laha, which was probably about 4,500 years ago here. So that's just exposed in a drain about 4 or 5 metres deep. And we can see that there is this constant frequency of lahars in the Whanganui catchment, but sometimes they get into other catchments as well. The Whanganui is mainly because the crater lake exits into the Whanganui. But if you get a large enough eruption whereby hot ash falls on the outer slopes of the volcano, then lahars can be expected in any of the catchments. And here's that enlargement of this old postcard showing all of them erupting in the 1890s. Well, we know the results of what lahars can do, and in this case we're looking at the Tangiwai disaster, when there was, estimated there were 657 cubic metres per second, and as the bridge collapsed, back up where the arrow is, because that's a road bridge in the photo there, then the railway carriages were carried downstream and very badly damaged, and a large loss of life. But we've seen it in even more recent times. This was a lahar that managed to get out of the crater lake and come towards the Whakapapa ski field, and here's what was the Government Tourist Corporation's kiosk in the ski fields in 1969. There are now no longer any buildings in the channels of the ski field anymore. They're all on ridges. And in 1969, one of those lahars that went down the Whakapapa had considerable impact on the Tongariro power scheme, because there's an intake here that takes water from the Whakapapa through to Lake Rotowaira. And so they immediately tried to close the gate, but by that time boulders and sand had accumulated at the intake and they couldn't properly shut the gate. So there was a bit of contamination there. And by the time it was down to this portion of the catchment, before it meets the Whanganui around here, there's also a water intake for Taumanui's water supply. Well, it turned out that these waters were still carrying their inherited water content from the crater lake, so they were highly acidic. And all the trout were killed down the river, but the eels were very smart, and they climbed out of the river and were seen wandering around the paddocks for several days before they jumped back in again. But Taumanui was able to get onto it pretty quickly and close their intake down, so there was no contamination of their water supply. But these are just elementary things that happen when one of these events occurs and you want to shut off your water supplies to make sure that the acid waters don't get in. In another case in 1975, they were still digging the tunnels for the Tongariro power scheme. This is just along on the desert road, and it was planned that there would be an open canal here with a U-shaped tunnel under the Whanganui River, which is flowing from right to left. And then there was a drop shaft here, taking the water then in another tunnel through to Lake, name escapes me, Mofanga, that's right, Lake Mofanga. And when this lahar came down, they'd not completed the work, and you can see the lahar just then came into the trench that they'd cut and went straight down the vertical drop shaft at about 4:30 in the morning, which was when the tunnellers were changing shifts. And so it was remarkable that no one was killed when this happened. Subsequently, of course, to reduce the risk, this is now all covered in, is a concrete pipe, and there's no opportunity for lahars coming down the Whanganui to get into that scheme anymore. So this is building in some resilience. Unexpectedly, in 1995, these lahars contributed large volumes of volcanic sediment to the upper Waikato River, and in particular this is the Rangipo Dam, which then began accumulating enormous volumes of sediment, and they had to then lower the waters and try and flush quite a bit of it out, which is what's going on here when this photo is taken, because there's no actual way in which they can open the whole dam across and let all this further downstream. But there were impacts on the ecology, because there's a lot of blue duck in this area as well. And above the Rangipo Dam is the Rangipo Power Station, and all this sand had come down and through their turbines, and those turbine wheels were just abraded by the sand, corroded if you like, to the extent that the owners of the station had to send those turbines to Norway, where they were coated with a very special nitride coating, I understand, before they were shipped back to New Zealand to protect them from something like this happening again. So there was a considerable loss of electricity generation during that event. And here at the Turarangi Marae, which is further downstream from Turarangi, we can see when the crater lake overflowed it took about 10 years after 1996 eruptions. We were expecting a large lahar to come down the catchment, and we can see here, as the lahar came down to this bridge, look at all the splash marks of the dirty water against the bridge. Had the flow been exceeded this, the top of the flow in 1995 was 3.2 metres below the deck of the bridge, and you can see in 2007 it was just touching the lower portion of the bridge. If it had been much higher, the bridge wouldn't have survived. So we can get loss of infrastructure when these events happen. And to show you at Tangawhai itself, in 1995 on the left, we can see that the lahar reached a level of 4.9 metres below the road decking. In 1975 it was 3.8 metres, and in 1953 it was only 2.2 metres. So when we knew that at some stage the lahar would break out again, as it did in 2007, there was a period when nothing happened, but eventually the road transport people were convinced to raise the deck level of the Tangawhai Bridge, which you can see here on the right they did by 2 metres, and we can see the splash marks from the lahar. This photo was taken on the 3rd of April. Here are the splash marks just here, and the old deck level was just there. So it wouldn't have needed too much more of a peak discharge, and if they hadn't done anything, we might have lost that infrastructure. In fact, in a paper we published in the year 2000, the Geological Society of America Bulletin, we did a study trying to put together the impacts of the 1945 and the 1995-96 Ruapehu eruptions. And it was just stunning, the difference in the impacts, because in 1945 it was the end of the war, and it was not a great impact at all, except on the alpine tourist industry. We estimated that the cost to the New Zealand economy of the 95-96 eruptions was in excess of about 130 million New Zealand dollars. And there's no doubt that it impacted on aviation and the electricity generation sectors as well, but it wasn't so easy to figure out what those costs might be. I remember flying from Hamilton to Palmerston North one day, and we literally flew through one of these ash clouds. It was very dispersed, and I guess the pilot thought he could see where he was going, but boy, could you smell the sulphur in the intakes. I put this in to show you that these historical discharges for lahars at Tangiwai over the last, should we say 150 years, shows you that that 1861 event was pretty big, even compared with the 2007 event. And we now estimate its peak discharge must have been in the order of 2,000 cubic metres per second, compared with the 2007 event, which was about half that size. And when we go looking around the Rangipo Desert in particular, we find we can compare these historical events, and I showed you that ditch that was dug by the forestry people. Well, if we calculate the volumes of those, we can now see that we're talking about that 450-year event must have been about 8 million cubic metres of material, and another one 500 years ago must have been about 18 million cubic metres. And so you ask yourself the question, what's going on here? Well, it would seem that in more recent times we can pick up these events, but they're mainly confined to the river channel, and as geologists, and we look back in time, the ones that are in the river channel are not preserved long term. And we're only seeing the big events that have occurred. So there'll be lots of little ones that never get preserved. But to get those large ones, almost certainly, we're going to have all this water in the crater lake released at once. Whereas in the 2007 event, it was the wall above a thick lava flow which collapsed with a height of about 5 metres. Well, when you look at Ruapehu, you can see that these are very old rocks here because they're all altered and have this yellow-brown colour to them. And on this eastern flank of the crater, just the crater rim here, you can see it's all black. There's none of these yellow-brown colours until you come around to this ridge around here again. And so almost certainly this is all very young here indeed, probably no more than 1,000 years old, and at times in the past water must have seeped away. We know water seeps out of this flank. Before the lake overflowed, the geochemists were picking up the acid waters down here, seeping through this structure. So conceivably that's something that could fail in the future, as it seems to have done in the past. It's not going to fail this way because there's a very thick sequence of lava flows across here, and so there's got to be a full eruption to get material going over this saddle to go down the western side. Well, over the years we've gone around mapping these deposits, and we can produce something we did here with Horizons, a lahar hazard map, which shows the frequency with which lahars come down these catchments. And we can see that the most frequent routes are down the Whanganui catchment here, and down the Whakapapa and into the Whanganui catchment up there. And then as we go back in time, those are red. As we go back in time, these are the next zone, followed by the lilac, followed by the light blue, which are less frequent but have occurred in the geological past. And also we can see them going down the Waikato River here, and there's a highly hazardous area where that delta is going into Lake Taupo. And in 2007 and 1995 there were some impacts there which probably impacted on the fishing as well. Well, in terms of these sorts of events coming out in this direction, what are the zones where they could occur? We can see evidence that in the geological past, a lot of them were going out to the north here, and before you get to Tauranui, there's an old channel that comes around here. It's very high, and it's been completely filled in by lahars, which has now been incised and beheaded here. So the river now goes around through Tauranui instead. And so we can see these lahars making their way down and preserved in the record to well downstream of Tauranui. And the flows would have continued on from there downstream. But the one route which seems to have been particularly active in the past are lahars that come down. There are three catchments here. In the north is the Waimarino, there's then the Whanganui Atiao, and then there's the Mangaturuturu. And in 1995, about the 21st of September, one of the eruptions from Ruapehu sent a lahar down the Mangaturuturu. Now, there happens to be a fault line here, and so anything that goes into the Waimarino, the Mangaturuturu, or the Whanganui Atiao, they all come together at this point, coalesce, and they can only come into the Whanganui Atiao. And it's probably one of the major lahar routes from Ruapehu when things come to the west. It's probably coming down the Whanganui Atiao that it gets into the Whanganui River rather than going all the way up around through Taranui. Also, of course, we know the Whangaehu River is particularly active because in the Tangawai disaster, debris and I believe one body was found down at the coast. The ones that have gone down into the area around Owakuni and Ratahi have not tended to extend any further for reasons we don't fully understand. So, and some of course have got into the Rangatiki as well. There are large boulders from lahars at Mangaweka, for example, which have been known for quite some time. Now, those are the lahar hazards, but there's also the eruptions. And the eruption on the 17th of June 1996 was substantial, went northwards due to a southerly wind and had a major impact on Rotorua. Rotorua's airport was closed and quite a bit of infrastructure in the central North Island had to be closed as well. This is the day after when we first got up there, and now it's more of a nuisance valley than anything else. So you could drive underneath this and you just feel the sand particles falling out of the sky. But the day before, some vehicles around National Park were just inundated by volcanic ash. And after taking this photograph, we went down to Taranui, where the car washing facility was making a mint with a great queue of cars. If we went back to 45, when it was still sort of wartime and people didn't really care so much about these things, we don't have detailed maps of where the ash went, apart from where it was and where it wasn't. But we were able to compile this map from Ruapehu where the ash fell in 1945. And you'll see that Whanganui's within the area of distribution, just as Wellington was, Palmerston North, Napier and the Bay of Plenty. So as the wind swung around, so this ash was distributed radially outwards. In 95-96, we were able to do things much more accurately. And what I'll draw to your attention here is first the magenta coloured lines. The magenta coloured lines were the eruption on the 11th of October 1995. Why did we have a tephra when we got a crater lake? Well, after the main eruption began on the 23rd of September, over the ensuing weeks, the activity in the crater kept spilling water out of the crater lake. And so by early October there was not much water left. This is a situation you really want because we'd like to have lots of little spills of water coming down rather than one big one. And on the 11th of October the water was no longer putting any sort of hydrostatic pressure on things, and a full ash eruption began in the middle of the night. And people woke up in Gisborne with about 1 millimetre of ash covering the Gisborne district, not producing too much of a problem. I'm told someone told me the azaleas did very well for a year after that because they just needed the sulphur. But you can see traces of that ash were found almost as far as East Cape and down just to the north of Napier. And closer to home, here it was 5 to 10 to 20 centimetres, 20 millimetres in thickness across the desert road. 3 days later, the wind had changed to the northwest, and this eruption occurred, sending ash across Tikakino, Waipawa. Here's 1 millimetre, 2, 5, 10. very thick along the Taihape to Napier Road in there. And the following year, on the 17th of June, when I said Rotorua was impacted, we're only looking at 1 to half a millimetre of ash here, but the impact that it has can be quite considerable on anything that's dependent on the atmosphere. Closer to source, we can see here it's 5 and there's 10 and 20 millimetres thickness in here. It had quite an impact on areas just on the west side of Taupo, for example, where the ash fell on roofs, some rain fell, and people's guttering was just falling off with the weight of the ash in their gutters. Then the wind changed dramatically, and the photo I showed you a little earlier was when the ash was going off in this direction towards Whanganui, and folk were out washing their cars. But a trace of it was found in New Plymouth, and it went up in towards Kawhia, Raglan harbours as well. And then it died down, and there was not much ash after that. Well, from a hazard perspective, this is the Desert Road on the 12th of October 1995 when we got up there. The Desert Road has been closed, but we were given permission to drive in and have a look. And if they had left the road open on this particular day, there would have been a horrendous number of accidents, because it had rained and the ash was all soggy and wet, and it was like driving through concrete. But the roads people were onto it, and very quickly cleaned it up, and the road was open within about 24 hours. But you only need ash of this order of thickness happening more than a few times, and people get pretty fed up and abandon things. And I just put this photo in to show you. This is Rabaul, a photo I took of Rabaul in 1998, 4 years after the eruption coated the town in a couple of centimetres of ash. And not only was it proving impossible for the airport, but certainly one half of Rabaul was completely abandoned, except for 3 hotels, which were the only high value properties really in the place, and they can't sell their hotels, they're all independently owned, so they kept going, but very difficult situation. And something that stunned me when I was at Mount Pinatubo in the Philippines in 1991 was to see the Clark Air Base. I'm only talking here about 10 centimetres of pumice, not Ruapehu or Taranaki heavy ash. But a lot of our modern structures are not built for any weight on the roofs. And we've had 2 cases in New Zealand over the last decade or so where hail falling on the roofs of a sports stadium in Invercargill and a supermarket in Tauranga just caused collapse. Up on the top there are aircraft hangars at the Clark Air Base, and the lower pictures are in an area where there was a little shopping area on the base. This was a supermarket. And this photo is taken just in here, looking across, and here we can see that these great big steel I-beams have just bent with the weight on the roof, and here are the big fans that were up on the top of the roof that have just collapsed in on it. So clearly long-run roofing is very highly susceptible to ash, and if it starts falling, you've got to be pretty quick off the mark to get rid of it. There can be benefits, and so I didn't want this talk to be all doom and gloom, and we were fortunate that before the eruption on the 14th of October 1996, a soil scientist by chance had gone along the Taupo Napier Road collecting soil samples. Well, what an opportunity, because we then had the nature of the soils before the eruptions and could see what had happened. And so, by fortune, here we have the condition of the soils beforehand. Here, this is the soil pH, and we can see that it dropped from, one dropped from 6 to 5.5, another one from 6.1 to about 5.65, and that was over a period of a couple of months, big drop in pH. And then we can see it sort of gradually regaining. And at the same time, these were the extractable sulfate in the soil. That's what the plant could get out of the soil, right? The extractable sulfate. and look at the humongous amount of sulphur that came out of the ash. So at this stage we immediately became supported by the fertiliser companies, because they realised that if farmers were to go and put their normal fertiliser on, they're going to have some sulphur toxicities. And so new recipes were devised over this period to allow for the fact that they had this humongous amount of sulphur. And this rise occurred for a period of about 9 months in the amount of sulphur in the soil before it either got bleached or utilised by the plants. And to give you, that's the soil, let me show you the fact that we also have plant material. And in the upper diagram we can see the amount of sulphur. It remained elevated for 9 months in the plant materials. The white dotted line is the thickness of the ash, so you can see at this point, distance along the road, this is where most of it fell. And here we can see these levels. The yellow line is the 4th of December 95. That's the past year sulphur concentration as a percentage. In 27th of March 96 it's dropped to the green line, and on the 21st of June is the red line. And even more intriguing to us was past year selenium levels were measured, and these are in parts per million. And we can see that, again, distance from the first site, when we get to the axis of the ash falling across the road, look at the humongous increase in selenium in the herbage, which then dropped over the following few months. So there are positives that do come at times from this, because of course a lot of the pastures in New Zealand, in the North Island, are deficient in selenium. People ask, well, how often might we expect these sorts of ash eruptions from Ruapehu? And back in 1997 we made the point that over about the last 1900 years there have actually been 19 of these tephras from Mount Ruapehu. So you can very quickly see, on average, we get one of those eruptions about once every 100 years. So you can feel you've had yours, all right, in 95, 96, on average. But each of these tephra episodes equates with the ash that was deposited over the 95-96 period, and so we think on average we can say that that's the periodicity of these scale eruptions from Ruapehu, providing it continues to behave as it has over about the last 2,000 years. If we go back 10,000 years, Ruapehu was behaving very, very differently, pumping out pumice across the desert road area, one eruption after another. But at 10,000 years ago, something changed, and it began producing these sorts of eruptions. Well, I thought I should finish with something really local, which is a number of you may remember that from time to time there are little clusters of earthquakes off Whanganui. And this is a map done by the seismologists showing shallow earthquakes in the 2 months prior to the 13th of October 2008, so 10 years ago. And these earthquakes have been studied by the seismologists, so this is not my work, over the years. And in a paper published in 1983, Garrick and Gibowitz wrote a scientific paper up on this continuous swarm-like seismicity, the Whanganui New Zealand earthquakes, and they had a number of conclusions, but I'll just draw your attention to the 4th one, which said these frequently occurring small earthquakes could be considered as a response to local stresses induced possibly by a hot magmatic inclusion. That's clearly written by a geophysicist and not a geologist. I mean, geologists wouldn't ever use this word. It's rather odd. But anyway, they were suggesting that one interpretation from this could be that magma is being intruded into the crust. Well, in a light-hearted mood, Dr. Trevor Hatherton, who was director of the geophysics division of DSIR, was talking to a civil defence conference and drew people's attention to this and said that if this is magma being intruded, should a volcano erupt off the Whanganui coastline, he would like to have it called Mount Hatherton. But not after himself. He pointed out that the first Lord Hatherton had helped establish the New Zealand Company, and it was to be named after him. Finally, let's also make the point that these intermittent ash eruptions have also had a major contribution to the wealth in the soils of the North Island. And the ones that are derived from the andesitic volcanoes are coloured pink in this diagram, and so we see a large proportion of Taranaki, of the areas upriver from Whanganui around what we'll call the Waimarino area and Whanganui. All these highly volcanic soils are ideal areas for food production. And they are some of the most versatile soils in New Zealand. And they need to be preserved for future food production for the generations to come. The soils nearer to Whanganui, west of Whanganui, called the Westmere soils, also have a considerable amount of volcanic ash in them. And probably when we get close to the boundary with Taranaki, there are some Egmont soils that come in as well, which have these andesitic ashes from the Taranaki region. And the result is that this ash weathers to some clays which are very open or holy, if you like, and this imparts the light, friable nature to the soils, makes them free draining. It means plant roots can extend down to 7 metres without any imperfection. And they are the premier soils of the country. And around the world we see this is where the densest populations occur, where we have the volcanic ash soils. And unfortunately in areas like Java with a population of 200 million, people get pushed up onto the slopes where it can become hazardous. Here we have the benefit of Tongariro and Egmont National Parks, and so the areas close to source are not going to be food producing. So if I leave you with the thought that when we look at the array of volcanic events that occur in the periphery of the Whanganui region, the most likely events are likely to be volcanic ash spreading across the district from time to time. The soils in this region demonstrate that this has happened in the past. If it's relatively thin, it will be of little importance, but once it starts getting above 1 or 2 millimetres, it can become a problem. And we need to look at any vulnerable pieces of infrastructure that could be impacted by this. I'll give you just one example. When I was giving a talk about this topic, and it turned out that I had the chief engineer for the Tararua district in the audience, and a few years later I met up with him and he said, when I listened to your talk and we'd had the ash come across Waipawa, we made sure that when we built Danivik's new water supply, it was to have been an open reservoir, and from that point on we made sure it was closed so it wouldn't be impacted by volcanic ash. So there are things that you can do beforehand to make your infrastructure more resilient, and this is of course the message that everyone's getting these days with all the storms that are occurring as well. Ash from Ruapehu might also be expected, but because of the wind directions I showed you before at altitude, you're actually much more likely to be getting ash from Taranaki than you are from Mount Ruapehu. And as far as the lahars are concerned, they will be most frequent down the Whangaihu River, but from time to time they will get into the headwaters of the Whanganui. And I'd leave you with this thought that if you go down to Landguard Bluff, near the mouth of the Whanganui River, there are all these sedimentary strata that have been uplifted out of the sea over the last 500,000 years or less, and plastered against the bluff is the deposit of an andesitic volcanic lahar about up to 50 feet above current river level, which clearly came down the Whanganui River at some time in the past we don't know when. But, and then even more remote, of course, the pumice eruptions, but we know, of course, that most of Whanganui's CBD has a layer of pumice that was deposited by floods after the Taupo pumice eruption. So we live in a living landscape in the North Island of New Zealand, and we know that these pumice things are rather infrequent, but the andesitic ones are the sort of thing that can occur once or twice in a generation and need to be taken into account when you're planning your infrastructure. So I think at that stage I've probably talked long enough and give you the opportunity.